Okay, good morning. So today we will discuss uh, mass defect, mass defect, nuclear binding energy, binding energy, um, packing, packing fraction, and binding energy per nucleus. Binding energy per nucleon. Okay, these are the four topics we will discuss. So yesterday uh, we have studied it atomic um, atomic atomic number of an atom is denoted by Z, right? This is nothing but number of proton present in the nucleus, nah? And mass number denoted by capital A, nah? So this is equal to number of proton plus number of neutron. Number of proton plus number of neutron in the nucleus, nah? Because and in the nucleus of an atom, inside the nucleus we have, suppose this is nucleus, inside the nucleus we have proton and neutron, nah? And outside the nucleus electrons are revolving, right? So atomic number is number of proton, okay, and number of proton and electron are equal, okay. Now first topic is mass defect, okay. Mass defect, mass defect, okay. Before that, what is the mass of proton? Mass of proton, mass of proton, what is the mass of proton? Okay, mass of proton in AMU. This AMU is what? Atomic mass unit, okay. Okay, we need mass of proton, right? Mass of proton, mass of proton in AMU. So 1.007, so this is the mass of proton, that is 1.007276447 AMU, nah? Or you can directly write, okay, just write AMU. So this is the mass of proton, okay. And again in nucleus we have proton and neutron, nah? So now what is mass of neutron? Mass of neutron, so you can google it. Mass of neutron in AMU. So this is the mass of neutron. Mass of neutron is 1.008665 AMU, okay. So this is the mass of neutron. Now mass defect. What is mass defect now? Mass defect, it is the difference between the sum of the masses of the nucleon. Okay, that means nucleon means nucleus or proton and neutron. It is the difference between mass defect is, okay, mass defect is denoted by delta m. Okay, delta m. So it is the difference between the sum of the masses of proton and neutron inside the nucleus and the rest mass of the nucleus. Okay, I will explain with example. Okay, let's take helium atom. Okay, in helium we have two proton and two neutron. Inside the nucleus of helium atom there is two proton and two neutron. And okay, so what will be the mass of helium? See, individually we okay 2 into, since there are two proton inside helium nucleus, and we know that mass number is number of proton plus number of neutron. That means, so atomic mass will be, or mass of helium will be, since there are two proton, so 2 into this mass of proton. So this one is mass of proton, okay, and this is mass of neutron. So 2 into, there are two proton, that is why 2, okay, 2, and the mass of each proton is this one, 1.0072747 plus again neutron. Mass of neutron will be 2 into 1 neutron is 1.00865. So you multiply these two and then these two and you add it, so you will get mass of helium. So okay, I will, okay, this is calculator 2 into 1.00727 1.00727 1.00727 1.00727 647 647 647. So this is equal to 2 point something. So here we will get 2.01455294294 plus this one, 2 into 1.0086 2 into 1.0086 1.008665 so we are getting 2.017 so if you add these two 2 9 4 5 6 and 8 5 6 and 8 7 8 9 10 11 1 against 1 2 3 3 0 point so we are getting 4.0318 AMU na? So we are getting this mass na? Mass of helium nucleus when proton and neutron are inside the nucleus. But from mass spectroscopy we are getting different mass of helium nucleus. Okay, mass of H see using mass spectroscopy we are getting this much. So this is the actual mass of helium nucleus. Okay, but see the actual mass is 4.0015. so the actual mass is lesser na? Using taking individual nucleon, that is proton and neutron, and calculating using those proton and mass of proton and neutron, we are getting this much na? But in actual it was found using mass spectroscopy that the mass of helium nucleus is this much na? So see which one is bigger. So this one is bigger na? That means some mass is missing, right? Some mass is missing na? So that mass is called mass defect. Okay, so this okay in diagram I will show you. Okay, there are inside the nucleus we have, let's say this black is helium na? Or proton. Okay, 2 proton and 2 neutron are there. 2 neutron, and it was found that its masses is 4.0015 AMU. Okay, but when we take 2 helium separately and 2 proton separately and calculate mass, okay, this mass, at that time we are getting 4.031. 8 1 2 3 4 1 2 3 4 AMU. So here see this mass is less than this mass is less than this one, right? So that means some mass is lost, some mass is lost. Okay, so that mass is called mass defect. Okay, so if you minus this one with this one, so you will get how much mass is lost, so 4.00155 5 6 7 8 3 0 3 0.0 AMU. So this amount of mass is lost, so that is called mass defect. Okay, see, suppose 2 proton, and okay 2 neutron. Okay, yellow is neutron and blue is proton. Okay, they are individual, okay, separately, so when they form helium means they are packed, okay, inside the nucleus. Inside the nucleus. So 4.0318 here when they are separate, okay, when they are separate at that time the total mass is 4.0318 318 AMU. And when they are together inside the nucleus, when they form helium atoms, at that time its mass was found to be 4.0015 AMU. So that means some amount of mass is lost during the process of formation of helium nucleus. So that amount is this one, 0.0303 AMU. So this amount of mass is lost. Okay, so this amount is called mass defect. Okay, why it is lost? Because during this process some energy is used, okay, to bind this proton and neutron together, so energy E is used, okay, to bind this proton and neutron together in the nucleus, so this mass is converted into energy, okay, this mass is converted into energy, okay, and we will get only this mass amount of mass only. The remaining mass, that means this one, is converted into energy. And we know from Einstein equation, Einstein energy relation, energy E equal to mc square, that means energy can be converted into mass. This energy can be converted into mass, or mass can be converted into energy, Here in this case, mass is converted into energy. Okay, so how much energy? So what is the mass? This mass, nah? This mass is converted energy. So we have to use this mass, nah? So this mass is called what? Mass defect, nah? Mass defect. So here the energy will be this mass defect into c square, where c is velocity of light, nah? So this is the mass defect or energy. Okay, and this energy is called binding energy. Okay, binding energy, because it binds the nucleus and proton inside the nucleus, nah? Okay, so now, okay, here we got this one, nah? This is the mass defect. Okay, so what? So binding energy will be okay. Now binding energy, okay, EB. Okay, suffix B for binding. Binding energy will be mass defect into c square, nah? So mass defect is how much? 0. Okay, this is for helium atom. Okay, I'm taking for helium atom because all this calculation is for helium atom, nah? So 0.0303, 0.0303. Okay, this energy is in joules. Okay, joules. 0.0303 into c square. So you find out this or you do this calculation, okay, and find the energy of or binding energy of helium nucleus. C is velocity of light. You know the value, right? Put the value and do the calculation. So here you will get the binding energy. And what is binding energy per nucleus? E, B, N. Okay, binding, B for binding, C for, N for nucleon. So binding energy per nucleon is binding energy divided by, per means divide, nah? Divided by nucleon. So in this case, how many nucleon are there? Nucleon means proton and neutron. Okay, so in helium nucleus there are 2 proton and 2 neutron, nah? So that means total number of nucleon will be 1 2 3 4, nah? Divided by 4, or you can write in place of 4 A, nah? Because A is what? A is mass number, nah? Mass number is neutron plus proton, nah? Neutron plus proton, okay, or proton plus neutron, nah? But in this case, this is the general formula. Okay, now for helium you have to put A is 4, nah? For helium A is 4. Okay, this is binding energy per nucleus. Now what is packing fraction? Packing fraction is okay, denoted by P. Okay, packing fraction is mass defect per nucleon. Mass defect, dm per nucleon means same, nah? The difference here, binding energy per nucleus is binding energy per nucleon. Packing fraction is mass defect per nucleon. Okay, so now you find this binding energy of this helium nucleus, and then binding energy per nucleus of this helium nucleus, and then packing fraction of helium nucleus. So here dm binding energy of mass defect of helium. Mass defect I have already calculated. This is the mass defect put here and divided by A. A is mass number, mass number of helium is 4, put divided by 4 and do the calculation and send me. Okay.